Hello, and welcome to part 1 of the module on patterns and frameworks for synchronous event handling, connection establishment, and service initialization. In this part of the module, we're going to be presenting the reactor and acceptor-connector patterns, which are key patterns for event handling, service initialization, and connection establishment. To motivate these patterns, let's talk a bit about our expectations of a web server. When we talked about the wrapper facade solution in the previous module, we focused on keeping things simple. We gave you an iterative solution that really doesn't scale. It was only handling one connection request, one GET request at a time from clients, which is absolutely not going to work in practice. One alternative approach people have historically used when they built web servers was to be able to support multiple clients simultaneously. And a very classic way of doing this is to use some kind of underlying operating system I/O multiplexer like select or poll or wait for multiple objects, and to run this in a single thread of control, and then to wait for something to happen on multiple sources of input, and then to handle all or part of the incoming requests before going on to the next request from a different client. Typically, when people implement solutions in this way, they tend to tightly couple a number of things. They tend to couple certain concerns. They couple concerns for event multiplexing and demultiplexing, service establishment, connection establishment, and service initialization. And those things all get glommed together with the actual protocol processing done, in our case, using HTTP. Let's take a look at a little bit of a code fragment that illustrates these problems. Here's a piece of code you might find in a traditional reactive style web server. And what you see it doing is it uses the select call to wait for either connection events or data events to occur on multiple sources of handles. That obviously hard codes us to using select, which may not be the right choice in all environments and all platforms. We're also still hard coding ourselves to some POSIX and Unixisms as far as how socket handles are defined. That'll be a problem if we try to port to other platforms like Windows. We're also using sequential linear search to look through all the handles to find handles where activity have gotten sources of events to come in. That'll take a certain amount of long time if there's a lot of connected clients. And then finally, we also tightly couple the protocol processing, the HTTP protocol processing, with the connection establishment, service initialization, and event demultiplexing. So how can we get around these problems? Well, what we're going to talk about here as a way to do it is to apply a pair of patterns that are often used together. These patterns are the reactor pattern and the acceptor-connector pattern. And we're going to use these patterns in order to be able to separate out the generic event infrastructure, service initialization, and connection establishment code from the protocol processing we do in the web server once things are connected. Let's talk first about the reactor pattern. If you take a look at this diagram, it illustrates the structure of the reactor pattern, which is broken up into a couple of parts. First, we have a role or a class called a reactor, and it's essentially a container. And applications or higher level services register so-called event handlers with a reactor via its register handler methods. And these handlers are typically pointers to base class objects that can be subclassed and customized to provide specific event handling logic. The reactor then squirrels away this information in some internal tables, and at some point the application turns the flow of control over to the reactor by calling its handle events method or run event loop method, at which point the reactor then coordinates with the underlying I/O multiplexer and synchronous event demultiplexing mechanisms that the operating system provides, which wait for activities to occur, which wait for events to occur from different sources of events on these handles associated with the event handlers. And when stuff happens, it returns, and then the reactor will dispatch the particular events to the corresponding event handlers by invoking their hook methods. Now, the application or the higher level service will have customized the core event handler base class, overridden its virtual functions, and then carried out whatever service-specific or application-specific processing functionality is needed to handle the events. If you take a look at this paper at this URL, you'll find more descriptions about the reactor pattern and ways to implement this pattern in practice. Here's a view that illustrates some of the dynamics of the reactor pattern. The dynamics are broken up into a couple of different phases. One of the first things we do is we typically register a bunch of concrete event handlers with a reactor. And the reactor often does a little double dispatching dance with those event handlers to get handles and other information explaining what those handlers are trying to do, what types of events they're concerned with. And those things get stashed in an internal table. Then at some point, the application turns the focus of control over to the reactor. It goes ahead and uses the demultiplexing and multiplexing mechanisms of the operating system to wait for events to happen. And when those events occur, it then calls back on the corresponding event handlers. Note the inversion of control that's taking place here. The reactor runs the event loop, it has the main focus of control, and it does callbacks to hook methods back to the concrete event handlers to get the work done. Let's now turn our attention to the second pattern in this group of patterns, the acceptor-connector pattern. The purpose of this pattern is to decouple the connection establishment and service initialization logic, which is fairly generic as it turns out, from the more specific, customized application or higher level service protocol processing that occurs once things are actually connected. As with the reactor, there's a couple of layers involved here from a pattern structure point of view. The core part of this is some type of dispatcher. We're going to be using our reactor, because they work together nicely, which is waiting for different kinds of events. In our particular case, the acceptors and connectors are concerned with connection establishment events, things that occur when a connection arrives or when you initiate a connection. There are several layers on top of the dispatcher reactor portion, and let's talk about the most important part. This is the part that deals with the connection establishment and service initialization. In this particular layer, we have three primary roles. We have connectors, acceptors, and service handlers. Service handlers are the pieces of logic that actually carry out the application protocol. They have a conversation with their peer. In our particular case for HTTP, they would be passing GET requests and POST requests and so on and getting the appropriate responses back from the server. The connector is the role that actively initiates a connection. And when the connection is established with its peer, then it goes ahead and initializes a service handler to do the actual application processing. The acceptor is the inverse side of this. It waits passively for something to happen. It waits passively for the connector to connect to it. And when a connection occurs, it accepts the connection, and then it goes ahead and calls to initialize the appropriate service handler. And now, once the acceptor and connector have done their job, the service handlers on each side of these different relationships go ahead and interact with each other and carry out their conversation. Here's a more dynamic view that illustrates how these different parts talk to each other. And to explain this particular diagram, I'll give you an example that's probably something you may be familiar with from everyday life. If you are an important person, or if you know an important person in an organization, that person often doesn't take their own phone calls. They have an assistant, a receptionist, who plays the acceptor role and will screen the calls and only pass the calls along if they deem those calls important for the service handler, for the person to handle. Likewise, if you're an even more important person in an organization, you may not place your own phone calls. You may have your assistant or receptionist place the calls. So the concept of a connector is the person who connects the communication. The concept of an acceptor is someone who accepts an incoming connection. And then the service handlers are the parties who are important, who actually carry out the conversation once other roles have done their job to get them connected. And this separation of concerns is basically there to make sure that we don't waste time of people and to refactor the generic processing so it can be handled at a lower level. Take a look at this URL for a paper that goes into more detail about acceptor and connector. Now that we understand the basic patterns, let's talk about how we could apply acceptor and connector in the context of JAWS. What we're going to do here is separate a couple of different concerns. We'll use the reactor to separate the concerns of generic event detection, demultiplexing, and dispatching. Some of the events we'll be dispatching will be those having to do with passive connection establishment and service initialization, and the acceptor will do that. Other events that will come after things are connected are events that actually correspond to the web protocol that we implement, HTTP 1.1, for example. In that case, we're going to have some kind of handler, some kind of service handler that will actually do the work once the acceptor factory creates it. Notice this particular example doesn't really emphasize the connector because a web server plays the passive role, but there are plenty of real-life applications where you need connectors as well. In fact, whoever's the active side of the web communication could be using a connector in order to carry out the connection establishment logic. So let's talk about some of the benefits and limitations of these various patterns. From the reactor pattern point of view, some of the benefits are these very strict separation of concerns. The infrastructure processing is done by some of the core parts of the pattern. You as an application developer don't have to write this code. You just have to know how to use it effectively. You just have to focus on writing your application logic. Some other benefits are that it's much more modular and reusable and configurable. It's easy to extend application or service-specific logic by inheriting from the base logic. You can reuse the infrastructure once you have a framework that realizes this pattern. Another benefit is it's easy to implement this pattern in a way where you can hide the details of the underlying event multiplexing and demultiplexing provided by the operating system to make your solution more portable. We'll talk later about ways we do this in ACE, but you can port this to many different platforms and extract and hide those types of details and encapsulate that variability from higher level services and applications. And another benefit you get here is you typically can have coarse-grained concurrency control. With a reactor, with a reactive solution, there's typically one thread of control that's being driven to call back into the application event handlers. And this particular thread of control can be doing its thing. And if you're writing an event handler, you typically don't have to be concerned about another thread of control coming along and modifying any data or state that you may be accessing. So it simplifies concurrent access. There are, of course, some limitations. If you don't have a platform that supports synchronous multiplexing and demultiplexing efficiently, then this pattern is not really going to work very well. It would be way too much overhead to emulate this with threads, for example. Another issue has to do with the single-threaded nature of this solution. If you have a callback that's being run on an event handler and that callback blocks or goes into an infinite loop or runs for an extended period of time, then you'll end up blocking and starving other connected clients from getting their work to be accomplished. And that could be a problem if they need to be more responsive. A similar issue with a single-threaded solution is we don't have an easy way to scale up to multiprocessors or multi-core. So as a result, if you're using a purely reactive solution and the arrival rate of new work is faster than it takes to process the existing work, there's no way to offload that by running it on multiple processing units. Another challenge you always run into when you start building frameworks and patterns that exhibit inversion of control is the more complicated debugging you have to be concerned with. Knowing how to set breakpoints, knowing when the various callbacks take place, require you to have some knowledge of the inner workings of the abstractions. And while that's not the most hard thing in the world, it does take a little bit of practice to become comfortable programming and debugging and testing in an inversion of control environment. Let's talk about some of the benefits of the acceptor-connector pattern. As with the reactor, things are more modular. You can tell at a glance what's the acceptor role, what's the connector role, what's the roles for service handlers. You can make things more reusable. It's easier to extend by subclassing or various types of parameterization from the base portions of the abstractions that implement these particular pattern roles. It's also more robust. You can't accidentally try to accept or connect to a service handler. You can't likewise try to read and write on something that's a connector or acceptor. The type system doesn't allow that, so it removes certain kinds of errors. And from an efficiency point of view, if you're using the connector portion of this pattern, which we haven't talked a lot about here, but if you read the literature, you'll find out more about it, you can actually invoke connections asynchronously. And the nice thing about asynchronous connection establishment is that that scales up very nicely within a limited number of threads of control to take advantage of the inherent parallelism in the operating system, the hardware, the network, the remote operating systems, and so on, to allow many connections to be running in parallel while only devoting a very small number of threads, maybe even just one, on the client side. There, of course, are some limitations. Typically, when you implement the acceptor-connector pattern, you have a framework implementation, and any type of framework has additional levels of indirection, various kinds of callbacks, and so on. And so you have to be sure that you can afford those levels of overhead. They're typically not on the critical path, but you have to think about this nonetheless. And there's always a space overhead incurred with frameworks for the most part. Another potential issue is that there's just more moving parts in an acceptor-connector solution. And if you're building a large system that's going to run for a long period of time, perfectly acceptable to walk up that learning curve and to master these other elements. If you're just trying to throw together a simple prototype, you might not want to spend the time learning all these different pieces. In my experience, sometimes these simple prototypes escape from the lab and we end up having to maintain them and extend them over long periods of time. So sometimes it actually makes sense to invest up front in learning the abstractions to make you a more effective developer down the road.